Start
Let's do
recording.
it. All right. So
Just go.
I'll start talking about. I have some links here. Let me. So F star. Let me bring up the website. Star. Let's just do a tutorial. Their website's pretty good. It's not complete, but it's pretty good. Here. So if you are interested, there's this nice website they made. That is essentially just like has everything you would need to get started. And I think it will not load here because I don't have JavaScript on Emacs. But anyway, I don't want to swap the screen. Anyway, um, so they have a very good explanation of what the idea of the language is. So I'll just start like explaining what are the concepts and probably go into a little bit of the pen types because I think you guys are like used to it, like you've seen at least. And then like we'll jump into the actual like code, and then I'll show like the syntax all the way around it, the tooling and everything. So Fstar is a dependently typed language based upon ML. It's a very interesting project because it has it is a research. It's a project being developed by Microsoft. So you can already expect that it's more pragmatic, right? So it's not like cock that it's literally useless. I'm joking. Um, so, and I was surprised to see that they actually use that in many other things. They're using, for example, like a Microsoft is using that on Azure, for example, for cryptography. And I had absolutely no idea they were doing that. They use it on cryptography on the Linux kernel. They have their own Linux distribution now. I can see the stuff, by the way. I saw some bubbles there, but anyway. So Microsoft is actually spending a lot of time and resources into making. And there's also a lot of people from INRIA involved, which are the OCaml people. So it's a very cool project. There's like a lot of people from Cambridge, Redmond, which are the two Microsoft departments, and INRIA involved, and some other universities, I think Argentina as well, and so on. So anyway, enough said. I think the main motivation that I think I got was, well, Nathan pushing. That was the deal. And also because I got turned off by Coq, because it is a very cool language, but I think it forces too much on you to just do simple stuff. And I don't think Fstar does that. I'll show you. It's like stupidly easy to get started. It's not easy to master, of course. Like there's a lot of alien topics, but it's a very good language to get off the ground. But also it has a very cool feature which is interop. So I'll just bring over here some topics. I have some links here. So it is based on top of this thing here. So let me bring this over. I know Wikipedia works. If it doesn't, okay. It's based on top of Hoare Logic. I don't know how to say his name, but it's basically from Tony Hoare, which is the guy that, well, it's more famous to create by creating no, the no pointer. He later regretted it, but anyway, he's a logician. He's a British logician, and he made this set of rules to basically design programming languages, correct programming languages. So he has this thing called the Hoare triplet, which is essentially just a. I don't think it loads the stuff here. Yeah, it does it. LaTeX. But anyway, he has this thing called Hoare's triplet, which essentially is you have a precondition, a post condition, and then you have a computation unit. And then if you have, that's why the triplet. So if you have a precondition met and you have this C, which is computation unit, then essentially you're going to have the post condition as true. So it's like a logic system based on that. And it's a very cool idea. And he was working at Microsoft. So I think that's why they picked a lot of the concepts on top of it. And he developed some this, which is partial correctness. So partial correctness is one requirement to prove that something is correct. You need to prove termination. For example, you prove termination, partial correctness, then you have a correct code. Um, So that's the first topic that I wanted to introduce. And by the way, I saw this one thing that's very cool. It's just a parenthesis here. There is this thing here. I'll just load it here. EWW called design by contract, and I've seen this before. And I was looking, dude, like this is really interesting. And this I discovered. Look at this. Look at this picture here. Oh, it doesn't load. Anyway, here. So, looks familiar, right? So it is essentially the same thing. And this was a thing designed by the dude who designed Eiffel. So it is a thing from OO from the 80s. So people were actually using it in the 80s. And before like OO was infested by like I don't know, interface hell and so on, and inheritance. But anyway, it's just a cool topic. I wanted to bring it over. It has many usages out there. And there's like a revival on this topic apparently right now. But anyway, so what I will, let's go to the main course now. Enough talking. So I'm gonna be basically coding and then showing you guys like what we can do with this. So I have my cheat sheet here, so just don't forget topics. All right. So the first one, I'm gonna talk about like the types. Okay, so it's dependently typed language, so that means we're talking about types with terms, types depending on terms. So let's start by defining some types. So the first thing, you need to define a module in Fsharp. By the way, it has first class support on Emacs. You can just start the process. That's it. So it's amazing. I'll show you. And then you need to do the module with the same name. So the name of the file is talk. So I just do module talk. And then, I don't know who is there. But anyway, and then you can just run and boom, it checked. You can ignore the thing. It's for my... it has a solver, which is a thing that basically solves the proofs, that does the proofs in the background. By the way, guys, you can interrupt me. I don't want this to be a monologue. But anyway, so let's define the first type. So empty, that's the first type. So it's the type, it's the empty set. So think of types here as sets. So this is a set, which is the empty set. So that's it. That's it. That's the empty set. So let's do another one. Type, I don't know, 17, which is essentially just...
Do you really need the equals there?
You can do something like... Wait, why is this wrong? End of the buffer. Wait a second. Unit. Oh, okay, never mind me. 17. This here. Yeah, in that case, I think you need the equals. Let's see if we can remove. Oopsie. Implicit assume new. Yeah, I don't know. Let's see. Yeah, you don't, but it complains. Implicit assume new. So let's just add it. That's how it was on the documentation. But anyway, I don't see much use for this. You may use for like some proofs. That's well useful. It allows you to do that, but I don't see. But anyway, you can do sets with only containing one thing, and this is the object. Sorry, this is the type set containing only 17 inside of it. So that's it. You can do stuff like more familiar, stuff like unit, for example. You just have one value. You can do normal discriminated unions, as you would think. So ABC, you can do A, B, C. So that's another set containing ABC. And then you have composite types, and here's how the fun starts. So let's make a list. So I'll call it my list because I think there's already a list. And the list takes a think of this as a quantifier. Sorry, a quantifier, no. A thing that goes on top of the list. Like think of the list. Oh man. Okay, like the problem on Emacs is that if you do like this, it already transforms the things. So like this is different. Anyway, so this. So think of this. So a list has two important operations, right? You have the new case, like think of Lisp. You have the new case, which is the empty list, and then you have another one, which is the cons, which you just like append new elements to the list. So let's do first the new. So the new case, we have essentially just a list with a, so that's the type. And we are lacking the the cons case. So the cons will have the head, which is just the value that you specified for the list, and we're gonna have the other list you want to join. So another. Let's not call it head. I don't think it's a good name. Elaine, whatever. It's also not a good name, but anyway. My list A, and then what this spits is just a my list A. So that's the type. So, oopsie, what did I do wrong? Okay, it was just evaluating. By the way, I think if I hover, yes, you see down there? Like if you hover over expressions on Emacs, it shows because some things they may take some time to evolve. So it just like shows it there, like pending, busy, or processed.
That's so cool.
That's very cool. And by the way, like documentation is in Fsharp, you would do like documentation for functions like with 3 things, right? Oopsie, let me just do this. See, with 3 things, and here it automatically infers that is a commenting block. So you can do ABC, blah blah. So that's very cool. Like for literary programming, I mean, that's very useful.
I have a quick question. Are those the name of the parameters? So LM and another?
Yes.
The
I
names?
can omit them, but they are the names. Yes. That's
Ah, okay. So it's not necessary. Could you just like arrow?
Yeah. Oopsie. No, come on. Oh man, like the symbols are a problem here, but like, yeah, they're a problem. But this is the tilde, okay? This is the negation. It converts here. But anyway, like it could be like naming in Fsharp or something like this in Nekoma. So
one thing, Magita, regarding the 17 that you have there, could you define a type that is a set that is either 17 or an empty string?
Yes, you can. You can do combinations of. I think I can do an example of that in a function. That would be cool. I can do that. Let me just do this division ish thing, and then we are gonna go there, Nata. I have a cool example that I can adapt. So okay, let's do a division. So by the way, you can do vol, like which would be to define the, like when we do signature files, right? You can define the signature of stuff here. So let's do division. So a division function, you take a numerator, right? And a numerator, well, it's just an integer. And then we take a denominator, which is also an integer. But there's a twist here, right? A denominator cannot be 0. Otherwise, but that's the division function doesn't assume that as a possible value. So we can do a refinement. A refinement is essentially just picking this expression and doing something that is like absurdly cool, which is denominator has to be different than 0. And that's a new set. So let me
just one thing, Magita. So far, it sounds like TypeScript. Refinement types and literal types.
Oh, yeah, it could be. It could be. Well, it's Microsoft, and so the names could be very similar or the same. Makes total sense. So let me just, oops. So let's see here. So, this, I'm not going to implement, like we don't need to, but I just want you guys to see, like, because I want to show this. This is what I think is important. Like, we can do operations like and filter the elements out of a set that we want. So, and that is the cool idea of dependent types, because you have basically things that are evaluated along when you are type checking things. So this should be, when I implement this function, this should be a function that does not accept 0 as the second argument for the division. So that's just the first example.
Question.
Go on.
So vol is for define quote unquote the type signature, and let is to define the implementation.
Yes, it's the same thing as like in Nekoma, Fsharp is the same. Like you just make a signature file, and then you can make the signature for a function, and then you just implement.
Yeah, okay.
That's the same thing. So let's talk about termination. I'll bring over that again. There's a very cool thing we can do with that. But termination is essentially, the base idea for the core logic of F star is that you can check termination. Well, otherwise all the logic would crumble, right? But how do you check that for like some random functions? The idea is to prove them. So let's make a signature here for Fibonacci, okay? Fibonacci. And I'm going to make it as Fibonacci, you would think, okay, like it's a function, let's do n. It takes an integer, and then it spits what? Spits an integer, right? But that's wrong. Because what happens when you give a negative number to a Fibonacci? That's not a valid number, right? The function doesn't accept that. So the function is actually natural. So there's a type net, which is 0 or more. So this. But that's also not, well, that F star is smart. And then it will infer that our implementation will terminate. So let's do our implementation first. So I'll do Fibonacci. That will take an n natural. And then we're going to spit, so let me just annotate. We're going to spit another natural number. And then we're just going to match, like a grug level. So we're going to match 0. We will spit 1. This is the first case. 1. That will spit also 1. And n. It could start with like 0, 0, or 1, 1, but who cares? And then n will do, I'm not going to do tail call, who cares? It's easier to see this way. So Fibonacci and -2. All right. What's the problem here? Like, if I run this, fine. It works. It proved to me. But let's suppose that in some case, but how is it proving? Like, how does it know that this function halts? This function terminates? And the way it does is that you have a total function, in this case, what they call total function. And the idea is very cool because it tests the function by rule inference using the type signature. So let's toy with it. So you see this return thing here? We can annotate this with this dot net. And then we can give a rule that is, by the way, by default, it's already being inferred, but I'm going to make it explicit, which is annotating the thing with some, with a pure expression. So this pure expression is decreases, and then I think it's this. And then the thing that it is decreasing. So this looks very strange, but what this is doing is basically saying, okay, keep on watch on n. And n is a natural number, so n is always decreasing, right? And then it will check, okay, so the base case, so 0 is 1, 1 is 1. And then what about this case? So if it is greater than 0 and greater than 1, so you can, if it is 0, what will happen here? Will be -1. So that's one flaw that it didn't capture here. But anyway, like, no, sorry, it's handled in the base case. Ignore what I said. So if you have 1, it's gonna fall here. If you have 2, which is the base case, 2 will be 0, and it will be 1, right? So that's the baseline, and then from that onwards, you just decrease the thing. So what it is checking here is that, okay, like I can just keep on watch on what is n and how n decreases, how n evolves on the computation. And since this is a natural number and I have a bottom, then I'm pretty sure that this thing will halt. What is the halting condition being handled? Yes, it is. 0 and 1. So that's fine. The function terminates. But then if we were handling something, let's try to make a... by the way, is it confusing? Did you guys get it?
It
I
is
get it.
okay. I just want to see one thing, man. What about if you change the n case to also sum up with n minus 3 to see if it will complain about
Okay,
it?
yeah. I was going to do change to integers, but there's also...
I also want to know how exactly do you describe more complicated properties? Because decreases is a very simple one in this case.
Yeah, there is.
Subtyping.
There is a list of all of them. I don't... You can basically do other functions here, by the way. So, like, for example, I think there is an example length that they give on their website that you can define other functions, other auxiliary functions, and then you can make the definition here using those functions. So this is like one function that's already annotated, but you can use other defined functions as well.
So, might as well ask now. In the division function, the denominator, if you're returning an integer, you have the denominator needs to be like a divisor of the numerator, right? I
Okay.
was wondering if you could define like that property and
Yeah,
like use that. Oh, that's cool.
you can. I think there is a cool example we can do with, Mersenne primes.
Yeah.
Mersenne primes, they take prime numbers, right? So I think they are 2 to m minus 1 equals to, no, sorry, 2 elevated to something n minus 1 is equals to a p prime number. If that rule holds, then it's a prime number. But then you have two sets involved because you have the sets of prime numbers to check like the numbers from, right? And those are two refinements. You can do an example. I think that's pretty cool. But let me just show Nata here because he said about this. So you see this thing here?
Uh-huh.
It could not find a relation. This means it could not find a partial relation, a well-formed partial relation that proves that this computation is halting at some point. It's an invalid case. It's a hole in your logic. Like your domain is not accepting that. So let's see. Expected type
It's
of
not
n,
true, right?
natural of or related to another number natural, but got the type int. So it's a random number that you weren't expecting there. By the way, in natural is just a refinement out of ints, so that's why it gets this subtype error. I think it's a subtype error. Yeah, subtype in check failed. Do you see? So it's out of a greater set. You can do other stuff here that will surely breaks. Like I think if you swap this to int, let me think. Yeah, I think if you swap this to int, it will pass. No, it will not. Okay, there's a notation here. Int. Oh, Victor's here. Hello, Victor.
Hello.
Yeah, okay, so it cannot prove the termination because, as I said, it doesn't have a bottom case. So in this case, the number here, like when we're gonna check, okay, it assumes the possibility of a check that you cannot take the inference forward.
Yeah, the negative numbers, right?
Yeah. So that's pretty smart. Let's just swap it back so I can proceed here.
I have a question about the division part. I'm
Uh-huh.
the typing newbie here, just to make things clear. So, in the case of division, every single place that is going to use this function has to declare that their integers are following the
Uh,
rule. How would
you
that
mean
work?
like if I need to do this, right?
Yes. Would you need like to define that? For instance, you have another function called foo that receives an integer. Do I need to define that that integer is also not a zero?
You're saying something like you have a annotation like ABC that takes, I don't know, an
An integer?
int that is, I don't know, let me just annotate it, and greater than 10, right? Something like this. And then it
Yeah.
just spits an integer. Or, I don't know, let's put bool, something like this. Yeah, let's just the integer. And then you implement it. You're saying if you need to annotate this here. Is that it?
Yes.
Nope.
For instance, I want to use the division function or something like this inside this ABC. Do I need to specify that my integer is different than 0? Or do I only need to match?
Okay, I get it. So
the-
on usage, right?
Yeah, on
Yes.
usage.
No, because here's the goal. Like, if you define that, if your number is admissible to be 0, then it will not match. Sorry. That's an unadmissible type that you have there. So we will not even let you do that. That's that's the idea of using this type, but this defining a type like this is preventing the possibility of you having that case.
So it's kind of like a chain. Every single function that is using division, it needs to specify that the denominator that you're passing as an argument cannot be 0.
Mm-hmm.
Okay.
Yeah.
Oh, I see. I see.
So I have a cliffhanger in the end. I'll leave it to the end. I think it's cooler. It's about domains, like shaping domains, and validations and everything. Like it's all useless if you have this, because you can do everything just here. So there's some cool stuff that you can do to prove termination. Like one example, I'm just gonna copy here, just from the website. They do an Ackermann function, and I think you guys seen it already. Which is just like a function that after I think it takes like a tuple of values m and n, and then after I think 4, 2, 4, 3, I don't remember. It takes like ages to compute. Like it computes and it's a proved function that halts, but it just takes too long to do that. And then you can prove it by using basically just decrease again with m and n, the tuple. So just the vals. That's a cool example. But let's do the. Wait, sorry.
Like on the division function, Breno was asking about the description that you that you was giving to the input, right? I think it's easy to see a parallel between that and a precondition. So you do that kind of annotation on the output. Would that be something like postcondition? Can you do the same kind of stuff on the output? Like,
Oh yeah, you can. Like here, right? You can even depend on the denominator. Like you can do. It's more complicated because you will need to do for all n. Let me. Yeah, for all n. Int, right? For all, we don't need to annotate this, but anyway, for all n on that thing, then it's admissible that the other conditions. Let's just do, I don't know. It's gonna do a crazy example here, like n is n divided. Where's the rest remainder here? Divided by this is equals to something denominator, something like this.
Is n the output?
N, yeah, n is actually anything. You know when you're doing math this,
Wait, so
a set of like,
so it's literally n, like as the
yes,
n in math.
yes, any, yes, that's
Okay.
literally the same thing. That's why you see the a that
Yeah, for all.
even converts that. It's parsing error because it didn't finish the thing, but it can refine. I have a good example. I think here is not a good one.
Okay, but
Let's
I
review.
want to continue Nathan's question. So let's suppose that I want to say that every single output of the division function needs to be, I don't know, even.
Okay, let me do a prime, because a prime is a good example, and you assume that you have conditions, right, for
Yeah.
the prime. So let's do one. So type, oops, yeah, that's what happens when you don't type correctly. Prime. So the prime set is essentially just a set, n, oopsie, which is just like natural numbers. Are primes admissible to be negative? I think they are, right? Anyway, for all, so for every number that you're gonna pick from a domain, so for every x in a random domain, that I'm gonna define to be, natural numbers greater than 0, like different than 0. So let's do this. My eyes are almost crying. So natural numbers which are different than 0, because otherwise we cannot divide. And then here's the trick that I think is the cool part. So dot. So this is the thing to start an expression, and then we can do something like what I was doing, like x, actually n divided by x, should be, should be equals to 0. Oh man, my nose is just irritated. Should be equals to 0. And there are two things we should handle in this case. That n is equals to 1 if that is true, or n is equals to x. Could be the opposite, but anyway, oopsie, sorry, x. I'm confusing the things here. This one doesn't matter. So either it's the same name. So if it is divisible, it better be the same name, the same number, or it is 1. If it is something else, then it's not a set. It's not a part of the prime set. So then, like, we can check some random stuff. Like, let's do a function now. Adds primes that will take a, b, that are both prime. And then it just spits whatever. And then I'm going to just add them. Okay? That's it. But then let's try to call the function adds primes with 3, 3. Parse error because it didn't bind it to anything. And I remember I could do this. Let me just do this. Yeah. I think I could do this as well. Yes. Okay. So I'm just adding two things. But if I change this to, I don't know, something that is not a prime number, like 10. Then so it is a number that it checked and it saw that it's outside the boundary. So that's pretty much like magic. Oh man, sorry. My nose. Any questions so far?
Yeah, this is pretty cool indeed.
Yeah. And I'm gonna show interrupt, which is even cooler because you can basically just define the types in Fstar, make the implementation in Nekoma or Fsharp, and use in Fstar again. And then like you basically have like the implementation in a normal ML language. So that's pretty cool.
Mageta,
Mm-hmm.
the first thing is that thing that you do to. Just a sec.
Okay.
It's almost like having like, I know it's not exactly the same as F Sharp or Campbell, but it's almost like having a functional programming language with proving support. I don't know how to say that.
It is, yeah.
Mageta, so that thing that you use to do the, I say like reinforce the invariance, the specification that you do with for all and stuff, is that what they call sigma types?
I,
And
I don't know. the name in particular, I didn't see any sigma types. I didn't see they naming it like that. I didn't see.
Okay. And the second thing is, in the case of the division again, if you do, how can I say, how do you call it? This specification that you do, like, is that refinement? How do you call it?
This is refinement.
Okay, so you doing this. Oh no, but there you don't have the for all and stuff, right?
Yes,
You doing the for all on the output.
yeah.
How do you know exactly if that's addressing to the numerator or to the denominator?
Well, you can specify which. You have the names. That's why the labels. You see, like you have access to them. So you can even make relationships as well. There is one thing that I think is very good on this case, which is a lemma. So a lemma is basically something that needs to be true if this evaluation is correct. So that is we can do for Fibonacci. Fibonacci has a cool lemma. Like, do you agree that if you take a Fibonacci number, it's at least equal or greater than u? It is, right? For every natural. So it's a dummy proof, but anyway, let's copy the Fibonacci here.
Wait, so you're proving the inverse of the property? Like n is decreasing, then Fibonacci of n is increasing, something like that?
You're thinking of the total, right? You're talking about.
Yeah, that's right.
Yeah, you can. You can do that. You have increase as well. But you don't need to do that. As I said, like it's already heuristic. Lemma is like lemma is kind of different. It's actually I don't know where I copied because it's gonna be different. So Fibonacci will take a number natural, and then what you're gonna spit is kind of different because you're gonna spit actually a lemma from this case. So lemma, which will be let's write the stuff we want using the function. We already have the function up there, so it's Fibonacci. So it should be Fibonacci. Oh man, Fibonacci. That will be Fibonacci of n is actually greater or equals than n itself. Does that hold? And then what we're gonna do is, okay, if n is less or equal to 1, then we return unit. That's what the lemma assumes you need to return unit in the case that are invalid. Otherwise, yeah, in this case we could rule it out, but let's just keep that. And then you can call it recursively as well. That's like so alien. Lemma. For decreasing the thing, and that's how you basically have the property being validated. So if evolved, so that's correct. You just proved this lemma on Fibonacci.
Question.
And let me just finish this real quick, Lem. And why does this relate to what you're talking, Lemos? Because Breno, because this is basically just making the inference proof for increase in this case. So it's the same thing. You can do like for decrease and a random case as well. Like I think they do in factorial on the website. I think factorial they do by decreasing, if I'm not mistaken. So that's the same thing. Golems.
Okay, so my question is, let's suppose that in the Fibonacci function, you put, I don't know, how do you call it, like a restriction or a constraint saying that n needs to be greater than or equal to 1, right?
Wait. Fibonacci.
Yeah,
Here, right?
instead of saying that n can be naturals, right? Let's say that n has to be greater than or equal to 1.
Okay.
Would you have to specify the base case now in the lemma?
Well, on the lemma, first of all, this function will not even evolve, right? because now you have a discrepancy between the state, the base state of the inference, and the value that you are calling recursively.
No, sorry. So make n greater than or equal to 2. That's fine.
Okay. So you want to skip the thing?
Yeah, what I want to do is to put the restriction that will make the base case never happens in the lemma, because this is already being addressed by the function that we are
here's
using.
the thing: you cannot even define the thing if the base case never happens.
You cannot define if the base case never happens.
Yeah, if the base case here never holds on the domain, then this thing itself cannot even happen.
Okay, that makes sense. Because I was thinking, okay, you were saying in the lemma that the base case is n less or equal to 1, if I'm not mistaken, right?
Mm-hmm.
But what if we can make the function that we are defining on the let rec already addresses this base case for us? I was imagining something like that.
So you wanted to see if the lemma can infer.
I think factorial, right? If you make factorial and you say that the input always needs to be greater or equal to 1, the factorial function is already holding the property that potentially the lemma will be talking about. That, oh, I need a base case. Yeah, but the factorial function that you just made is already saying that the input needs to be greater than or equal to 1.
Yeah.
So I was thinking, okay, what happens with the lemma then? Because this lemma is recursive as far as I understood.
You gotta think that, yeah.
If you remove the base case for it,
yeah. If I remove the base case, then it's not even permissible operation.
Okay, so both. Okay, so there isn't some strong relationship between the Fibonacci and the Fibonacci lemma. They are kind of separate.
Yes. Yeah. They are in the sense that you're proving a property for this function.
Yes.
Right. So you can do this to prove like specific statements that you did not cover here. That they're not necessarily wrong, like things that will happen wrong, but stuff that you want to increment. In this case, we kind of could. Let me think. We could prove, like, this is a dumb lemma, but we could prove something like, if you're using something like every number multiplied by 2 is odd, is even, for something like this. Like, you could do something like this, using a lemma.
Okay.
And
Thanks.
that would be more useful, but this case is kind of dumb. There's one thing that I remember now, I was talking to Nathan, and he mentioned like different types, right? You can do multiple types. Like, which type? I'm out of names, so just give me ideas. Let's do kind of, and then I'm gonna basically just input like I don't know, string, whatever. You can totally see my Emacs is broken. And then since I just remind terms, we're talking about terms here, so I can basically do something like kind of equals to, I don't know, ABC. Then I'm gonna split a type. So what types do we have here? Okay, let's do unit and ABC. Oh, 17. So then ABC, else 17. Okay, so that's our return type. So it's either one of those. And then we have a match here that basically picks kind of with, dude, there's something very cool that I want to go there. But I just not gonna rush. So I'm gonna check if it's again that. It's just a stupid case, but anyway. I'm gonna speed B, whatever. And then anything else, I'm gonna speed 17. So you basically have 17 of type int.
That's so crazy, man.
Yeah, it is crazy. Yeah,
let's just boom. I don't know what I did there, but let's just speed.
I think it was complaining that 17 is actually an integer, so probably you have to wrap the 17 with the 17 type. Yeah, this is dependent types. Cool.
So that's cool. You have an expression building which type you want to yield. So you're actually evaluating that. So there's one thing here. I have this kind of stuff that I was reading, and I was like mind blown. I was talking to Bene today. Let me just copy this thing here. So there's this thing called universes. Have you guys seen it? So remember we were talking about identity, applying identity. Okay, here there. So there's this thing that I discovered why, like you can terminate. So let's go slow, okay? So imagine we have a thing called the universe. Like think about this. You have the type. So what the heck is this, man? Like it's a type that contains every type, like Russell's paradox, which I prefer to call Plato's cosmological argument. But anyway, and then what we're gonna have here, I'm gonna make a type called universe. That's how they do it in the tutorial. Universe. So I'm gonna make universe. Make universe 0, whatever. So oopsie. Can we see? Yes. So you see here. Can you guys see?
Yeah.
So we have now an infinite countable set that defines universes of types. So what does that mean? By the way, let me just do. You can annotate it like this as well. Oopsie. Type equal type. I think most often you will see like this. So oops. So you can see there that it has the 1. It's the same thing.
Wait.
Okay.
If I'm not mistaken, when you use let, you were defining some sort of a value or implementation. Is that correct?
Yes.
So you are defining a value in which
Type.
is a type.
Yes. That has the type.
Okay.
That is very weird.
Wait. Universe 0 is a value that is a type, and universe 1 is also a type, but has a type
Yes.
also.
Yes.
Okay.
Also, dude, this will get way crazier. Like, see, this is how you enumerate it, by the way. It takes this parameter here that is the ID for it. And then just take a look at this. Like, we have ID 0. So, what is this relationship? Can I do something wrong? Oh, I'm stupid. All right. So, what is it doing? It means that whenever you define a thing, you see this 1 plus something, it is getting the next one. So what does that mean? That is just a way to say, okay, like from the world 0, when you actually assign this thing for this other garbage, then it's gonna be 1. You're gonna increase. That's why it's countable. You have this variable in it that is basically keeping track on which universe you are.
Wait, so it is addressable also?
Addressable? What do you mean by addressable?
Yeah, imagine that you have an array of universes, right?
Oh, yes, you can. Yeah, I get it. So, for example,
how does this make any sense, right?
this is to prevent Russell's paradox. I'm gonna show how. But anyway, like you can just imagine that you start on 0, and then you just go until like not until because it's infinite, but you have like this. Oopsie. And you can do like sorts of crazy stuff on this, man. It's not even
So
start.
anything that can describe me is like one universe above. And in other languages, we have like, I don't know, universe 0 are terms, universe 1 are types, but there we have like n.
Yes.
Holy fuck.
And then, dude, like think about this. You let's try to define. So there's this thing that you cannot define a type over itself. So let's do a universe over itself. So otherwise you would have the Russell's paradox. So when you try to define this, I'll just try to remove this. Actually, I'll keep this. I can send you this code later, but anyway, just comment this. And then we're gonna do, okay, type universe of degree, I don't know, 10. Oopsie. Is of type of degree 10. What will happen?
Wait, Magetta, before you continue, I need you to repeat again what universe 1 is. Because I think that I already lost
Okay.
track of it.
Okay.
Because
Okay.
Nathan said that universe 0 is the universe of terms.
Yes, because he's talking about.
No, I understood what he said. And that makes sense to me, that the first universe is the universe of terms, and then the next is the types, and then the next is the kinds, and so on and so forth.
Think of an arrow type, for example. What is the universe of an arrow type?
Isn't universe 2?
It's the max of the universes of the input and the output. Do
Yeah,
you agree?
okay. Yeah, okay, I agree.
So that's the building of the universes.
No, wait. I understood that. What I want to understand is the notation, like the syntax. Because you're saying let universe 1 column type equals type. Why is that the universe of, oh my god, universe of types, like in the sense that the 0 is the terms?
You're talking about this.
Yes.
So the question is, why is this
The
the
universe
same as
of
this?
types, in the sense of terms, types, kinds.
Why is this the universe of types in the state in terms of?
Yeah, universe 0, as far as Nathan said, and I understood that way, is the universe of terms.
Yes. Like
Okay,
natural, blah blah blah, whatever.
and then I want to understand the syntax. Why this syntax is telling us that this is the universe of types? That's what I kind of got lost.
Why is this syntax telling us that this is the universe of types?
Yeah.
I didn't get the question then.
It's because universe 0 is
Mm-hmm.
saying let universe 0 equal type. For
Yeah.
some random reason, Nathan understood, and that makes sense for some random reason in my mind, that universe 0 is the universe of terms.
Yes.
Okay, so I want to.
Okay. I think what's that confusing is you cannot have the same. Like imagine you have a type that set. I'll stop using type. I'll use the word set.
Thanks.
You have a set that contains everything. So if you
Yes.
have a set that contains everything, then does that set contain itself? Like that's the Russell's paradox.
Yes.
But the only solution, the only escape hatch out of this is that okay, like there's no such thing as this set, but there is a set greater than this set that will enforce a priority over me. So I have the universe 0, and then I have universe 1 that engulfs universe 0, and I keep going. That's it.
Can you tell me what it would look like universe 2? Write it down.
Okay,
I think
let
I
me
would
think.
I think I will understand if you write it down that down.
Dude, you're asking for creativity to write to write
No,
that. Let me
not
think.
creativity. I want to understand the syntax because I'm not
I have
understanding.
one.
Lemos,
Go.
is the line 4 the one that you are like confused about?
I think both
One,
3 and
four,
4.
3 and 4.
Yeah,
Magita, doesn't the line 4 has like implicit stuff?
This is the same thing, man.
No, I mean in the sense that you are not addressing a specific one, right? If you were like
No,
the line
no, it's
4, would
just
be an
random.
error, right?
Yes, if you see the thing, it's one plus a variable. I need to evolve.
So yeah, if you were like annotating a
Good.
way to give more semantic, would be like, oh, equals type n, but the thing after the column like n plus one, right?
Yeah, dude, I'll go do an example with the identity that I think is better because I use the I and then you can see where. So I think it's better.
okay,
Let's
anyway.
do the identity type.
No, but
Oh, by the way,
continue with your universe 10 there.
yeah, okay. So this is an example like you cannot assign the same type to itself. So this needs to be 11. Then it works. You see? Just increasing. So let's do identity. Identity is a cool one. You can do stuff like, by the way, let's just do this. Oops. So let's annotate. So what happens when you do this? What is the type of that? That's the 0. That's where integers live. Like they are the most primitive garbage. I need to stop using garbage for everything, right? Anyway, so that's it. So let's do the identity because I think it takes another type, so we cannot be on 0. So let's do identity. So identity, we take a type and an arrow, right? And then it's an arrow of t to t. That's it. So we're gonna do type. Let's not annotate anything. Just do this. Of t to t. And we're gonna do fun. Let me do it here. Fun. That will basically pick the thing, t, the x, and it will just spit x. So that's pretty easy to define. Oops, what are I doing wrong? Let me just see here. Not doing any bullshit, am I? No, that's right. Oh man, stupid. This is just the annotation. I'm dumb. We copy from here. Oops. Okay. That's easy. Okay, so I forgot about something. That's why I got confused. Let me see here. I think this would make more sense if I put it this. They also call this polymorphic type for polymorphic universe polymorphism. Which is basically this. Like you see this L, and then you can just do a counter L plus 1, which is that thing that is like this. Because we don't care about what that is. But in this case, to enforce the relation we want, to make it explicit. And then I have the type, which is in this case universe. So this is just to assert. This is, by the way, you have two kinds of assertion. Equality. This is equality on type terms, and you have equality on normal terms, on values, I mean. So that's it. Okay, but let me bring equality here, identity. Just the type. Because that's gonna be the type annotation for identity. That's why I was copying. I was like, dude, what am I doing here? So the type of identity is just a type. So it spits a type of L plus 1. So one universe above. It takes T, which is just a type of the current universe you are. And then it takes this T, and then it spits this T. That's it. Spits the T. Looks like I'm talking about T. But anyway, and then we can just annotate T here. Identity type. All right, so that's it. Now, what we were discussing the other day is that if you apply identity to identity, that would lead to an infinite recursion, but to an indecibility, right? But in this case, it doesn't, because you gotta think that the types they're talking about here, they are in different universes. So identity, I'm not gonna provide any types just to let f star infer. And then you can just apply identity again, and then it just works. It checks for you. In fact, you can do this. Oopsie. And then it matches the type. So it's an identity type of type U something. So some random number. You don't care. I'm just going to leave it like this. So let's, I'll try to make it explicit now. Let me open the thing because, man, this annotation is just horrendous.
Just to give Breno a little bit of context, because he dropped off and then he came back in. Apparently, Breno, the F star allows you to have multiple layers of like I'm gonna use very loosely the term kinds, right? So you have like star, 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 and then in here you can have an arbitrary number of like one thing encapsulating the other, the other, the other, and so on. So you can have like what he's calling an universe. Is kind of what I'm understanding is like a kind
everything.
stuff. Yeah, but
Yeah.
But
That's not.
you are renaming every single time you add like a kind to like star to star to star. You are calling this a universe. So another star, another universe, and so on. That's kind of what I understood. And then he's showing us that you can use identity on identity because we discovered that Haskell can do this, but OCaml can't, which is cool.
This is cool. Just to rub on that face. This is the value, and this is the actually the first one I think is the annotation only. But anyway, like it's a type of this universe, so that's why it is inferring this, because it doesn't insert any useless variable. And then it just like setting the precedence, so it's gonna be one step ahead of the universe that you currently are when on the application. So let's see if it didn't do. So there it is. So you just proved that this thing halts, and you can implement identity on identity, because the types here, there are different levels. So you have an instance of identity one universe less than the universe that you currently are. So you can do that because, well, there's no conflict between the two. That's it. I have a cool example of interrupt. Do you guys have time? I don't know how much time we have.
I have 13 minutes.
All right, so that's enough. So I already made it here. Let's see.
Just to be sure, so what you're calling interrupt is having a bunch of F# or OCaml code, throwing that at F star, F star proving stuff and saying that you're good to go?
Yes, sir.
That's pretty cool. That's definitely an advantage, I would say.
Prime and I'm gonna use OCaml because F# is more shitty on that regard. Let me just start again. So we have this thing here, which is the F star thing, like the interface thingy. And by the way, on macOS I cannot print. I don't know why, but I can't. But if I run, it just okay. So this function accepts primes. If you look at the type, you see the type down there on the mini buffer here. Takes a prime, and then I pass in 4. So it's actually checking for me. So let's go on the other file, which is prime.fsti. So this is the signature file it gives to me. And it's essentially the same thing, you see? With the add primes here, the annotation. And then I made this module here in OCaml. Oopsie. There it is. Which is just doing the thing. But notice, for OCaml, I don't know if I have the LSP open. LSP. Come on, OCaml. Come on, man. What egg mode? Anyway, it will infer just as integers. Like it will get, it doesn't get the refinement, like on the host language, you mean, like where you are implementing. The only goal of this is that you can use like OCaml modules and a bunch of stuff like I don't know, sys, Unix stuff, like you know, like from like I don't know, you can use Unix, yeah, and do a bunch of like stuff from Unix. Oh, it's all chopped off. Yeah, you can like use like most of the functions there. I don't know if the limitations I didn't reach. I suppose F# will be worse in that regard because, well, you have a bunch of stuff from .NET. So I think most of that stuff will not work. But you can just define it here. Like you just make a signature in F*, define the stuff. You can implement the thing in like another ML, and then you're good to go. Like you can just go back to F*, and then you just test, and then everything works. So that's pretty cool.
Wait, so you're using a star just to prove properties about the functions and OCaml for the implementation itself?
Yes.
Prove that a container can't use more memory than like make your own
Oh man,
provably safe
no.
runtime.
Let me bring this over right now.
Okay,
You
but I
touched
have a
on a
question
good.
then. So
Okay.
using F star with interop only means that you, okay, I want to be aware of the properties of this function that I'm making in another language, but you
Mm-hmm.
cannot borrow like the safety part from F star to the host language.
Yeah, it's one way. Like you're
Okay.
doing in F sharp in Nekoma or F star. I don't know if you can do the other way around. I don't think you can.
No, no. What I want is like, wait. You said that you can grab from F star to the host, right?
Definitions, yes. Like you
Okay.
can use them as functions. That's what I'm saying.
Yeah, but I was wondering like, okay,
Yeah, really.
I want to know if this function, I want to have more safety on this function. And then I throw it F star, F star proves the things to me, and then I can grab that back to the host. Because like that, I was imagining something like that would be
Grab, think of
outstanding,
grabbing
right?
a value. I mean, think of grabbing a value. I don't think you can, like directly calling,
hmm
But no, actually, calling, I think you can. Like, you can call, as long as you have the signature, you can call other defined F star functions inside the host language and use them as such.
Oh,
What
okay.
you cannot
Wait,
do, because who will be evaluating is actually F star. It's not like OCaml.
No, yeah, in
So
this case makes sense what you said. Okay.
yeah, what you cannot do is like, okay, just call the OCaml compiler and like expect it to understand stuff.
Yeah, exactly. That was what I was meant. There's no way it can do that.
Yeah.
Because the
But
first
but
here,
application. Okay, go on, Nathan.
isn't extraction what Lemus wants?
yeah,
Like,
that's extraction.
uh,
Because the first thing that came to my mind is, man, everybody complains that we are not proving stuff when you're doing type classes in Haskell. If we could do this F star
There are
stuff,
type
we
classes here,
could
by the way.
prove.
There are type classes in Fstar, by the way. There's a section dedicated. I didn't read though, but there's a section dedicated for it. There's this subset of Fstar that actually Fstar is like kind of weird because uh, there is like a subset of it that you can compile to Fstar, and then Fstar compiles to F sharp, OCaml. Um, you can do that. You can do that actually. You can. Yeah, you can produce the code from Fstar and then compile on OCaml just fine. But you need to produce the code first. You can produce on WASM and C as well. I think yes, I think C, and I think they're working on Rust so far. I remember seeing this somewhere. But dude, look at this here. This is essentially a subset of Fstar that you have see these types here. They're all like defined on low star on the low star module inside Fstar. That you essentially are doing like low level programming, like low level, I mean C. That's not really low level, I know, but you are doing sort of like safe code in C with the performance of a compared to efficiency code. And you can do like malloc stuff, realloc and everything using the safety of dependent types. And that to me is like absolutely cool. Like, man, let me go to the F-Star tutorial. There is a like on the introduction, I think they give you a taste of what you can do with that. I was just like drooling because that was like, oh man, so much of my life was in vain. No, not so much, but anyway. Uh, Let me just get it here. Just a second. Pink introduction. Dude, it's like one of the first examples should be here. Oh, here it is. So paste here. Paste here on the talk. So it's gonna fail because I'm not importing stuff like uint. But just look. This is essentially just C code that you're guaranteeing. Like you see these requires, ensures, like these are other things that you can do definitions. ST, I think you need to import open star. Yeah, need to the
Okay, this is kind of
stuff.
a stretch, but I want to ask it anyway. So
Hmm.
can you can you do in F star something like, okay,
Hmm.
this function will do some stuff, but we will allocate some memory, and I'm guaranteeing that after the function is done, after providing the output, the memory is already freed.
Yes.
Man, this is so cool.
Yeah. So actually, I think I don't know about this case in particular, but you can define,
Wait,
for example, that you're not accessing. I don't think this case you mentioned in particular works because that's like
Oh, okay. Because I
I don't
would I
know.
would start
Depends.
saying, man, who needs
I don't
borrowing
know.
in Rust
No,
then?
here. No, here. Depends. I don't know how this free function works. Depending on how it works, maybe you can. But like for example, if you allocate a thing and forbidding you from accessing like things out of boundary, like you can do in C, I don't know, with a pointer. You cannot. Like that kind of stuff, it prevents you from doing that.
No, that's already
So
super cool. But do you
yes.
know something about what I said, Nathan?
wait, can you repeat what you said?
Yes, yes. So I want to say, I want to Fsharp to guarantee to me that I will allocate some memory in the beginning of the function, and I will return the output with the memory that I allocated already freed. I want to have a property that says at the output every single piece of memory that I allocated in this piece of the block, in this function specifically, the memory is already freed. I don't have to care.
Man,
Maybe you can define a lemma. I don't know. Maybe you
I'm
can.
not sure if you can really define those things because they don't have really to do with values and types and stuff.
Yes, that's what I
No,
was
but
They
thinking.
are not.
if you can prove that I'm not gonna access any external memory that I allocated, I don't see exactly why you can't say I'm guaranteeing that the memory is gonna be freed after. That sounds like an extension to me or something like that.
Yeah, for me, it looks like the kind of thing you would not be possible to do because it's not the result of, oh, I'm applying some expression, it has some specific type and properties about this type or value. It's more like different actions, you know? So I think that what would solve this kind of stuff and is kind of what they have in Rust is things around and including linear types. It's something around that. What Rust does is that it does implicitly, right? So you could also do a type system that has like linear types and shit, and he would guarantee that, oh, every time I use that thing here to allocate, I will use it somewhere to deallocate.
Yeah, well, I see what you mean, but uh, um, I got that impression from what Magita said. Like, F-star can
Uh,
guarantee you that you're not uh,
I don't
manipulating
know
memory.
actually, man. I'm not sure because, well, how do you check if there is like if the memory is free? I don't know how that works. I don't know how they do that. Depending on how, then yeah, you can maybe. I don't know. I'm looking here. Dude, there's a giant specification, and I don't even know how this works. Like, so
No, but the fact that you can have control, like granular control of low-level stuff, with like proving stuff, that's already super cool. That's already like cool enough.
uh, the problem is like searching this because most search engines they remove the like asterisk because that's just like trash. Uh, free.
But that would be like amazing. That was basically a slap on Rust's face, right? If you can just say like a mathematical property about freeing or not freeing memory, the borrowing system from Rust will be
Yeah,
like,
like there is a.
who am
It's
I?
actually.
Right?
But think about this, man. It's actually a double-edged sword if you think about it, because the more you start to define stuff uh, like you're making a lot of proofs and everything, but I think the more you start to dive in, the more difficult it will start to for you to do the rest of the stuff. You know.
Oh yeah, the proofs can
And
get
it's
really
very
huge.
unproductive. It's correct. Like you can. By the way, it's not preventing all the errors. Like you can still do bullshit. Like when I was doing the Mersenne primes, I was doing something and I left a hole in the domain, and it couldn't infer like that it had the hole. But when I was trying to call the function, then it noticed for me. So in that case, it got. But like that was something that could totally be unnoticed in that case. Uh, And then like okay, there's those situations, and I think there's a problem, which is you start to get really unproductive by doing this. So why do I think there is this interoperability, and why do I think this is a big thing? Because you just want the type safety of like basic types annotations for functions, but to code, you're not gonna want to code on this, because well, you're gonna be proving a lot of stuff every time. It's gonna be it turns into like cock a hassle.
Yeah, no, I
Because
totally understand that. But I had to ask because it when you showed this piece of code with malloc stuff, I thought, okay, maybe this is too cool in the sense that I cannot ignore it anymore. Anyway, we already passed my time here. I have to go. So, uh,
I
anything else,
stop.
Magenta?
No, that's it. There was plenty more stuff to talk, but I was thinking, man, if I start talking about like everything, I'm not gonna have time. So
Yeah, no, you can
that's it.
always schedule a part 2 or part 3 if you want. Feel free.
Yeah, I could talk about how to make for by the way, our simply typed lambda calculus interpreter without systemf would be like stupidly easy on this. Like it's most of the conditions we just check is like really stupid. We could
Uh,
do that. I don't know.
no, feel free,
Anyway.
man. If you we you
Or
have
I
the
can investigate.
option.
Yeah, I'll think about it. I can investigate more into Low Star. I don't know how it works, so it could be another sequel.
Okay, I will finish the recording now.